Hi, I'm Martin, and I'm talking about near-optimal deterministic single-source distance sensitivity oracles. This is quite a mouthful, and I explain what I mean with that. In the area of fault tolerance, we want to maintain a graph property under edge failures. In this example, we have the shortest path between certain pairs of vertices, and it might be that if an edge fails in the graph, that the distance between some of these vertices increase. And we want to prepare for that. Specific to fault tolerance is that we know the maximum number of failures in advance. This is also the main difference to dynamic graph algorithms, where these failures may arrive one by one, but their number is potentially unbounded. And as a fault-tolerant data structure, we want to pre-process the graph once into a small structure that we can then query when needed. The query is a set of failing edges, at most alpha for them, and we get as answer the property of the graph G minus F, where exactly the specified edges fail. In this talk, we are interested in the distances from a distinguished source vertex S, and we only have to prepare for a single edge failure. We call this single-source distance sensitivity oracles, or single-source DSOs for short. But note that the target vertex T is part of the query, so we still have to prepare for all replacement distances. Closely related is the problem of single-source replacement path, SSRP for short, where we are given the graph with the source S and have to compute the replacement distances for all targets and failing edges E. It is well known that the relevant replacement distance are only those with edges on a shortest path tree rooted in the source. Because if we fail an edge outside of that tree, it doesn't change any distances. So the output is at most quadratic. And on undirected graphs, which is the setting we are interested in, the fastest combinatorial algorithm is given by Schirneck and Cohen in 2019. It runs in number of edges times square root the number of vertices plus n square. It is randomized and works on weighted graphs. If you are willing to use fast matrix multiplication, you can do better than that, as shown by Grandoni and Wasilewska-Williams, who gave an SSRP algorithm that runs in capital M times n to the omega, where capital M is the maximum integer weight in that graph. And under reasonable assumptions, these running times are tied up to subpolynomial factors. The first one, at least for combinatorial algorithms, and we also do not expect any huge improvements for the second one. And of course, any SSRP algorithm, by just storing all the n square answers, can be seen as a single source DSO with quadratic space and constant query time, because you can then just look up the answer. It is known that the quadratic space is not optimal. Gupta and Singh gave a single source DSO with n to the 3 halves space. Their construction is randomized, combinatorial, and also works on unweighted graphs in time mn, so the number of edges times the number of vertices, which is a bit larger than what you do for SSRP. And they have a slightly increased query time to logarithmic. The fastest deterministic single-source DSO was given by Bilò et al. And has the same preprocessing time and space, but it has much higher, so polynomial in n query time for being deterministic. And we essentially want the best of both worlds. We want low query time, we want lightweight space and fast preprocessing. So what we do is we essentially reduce the construction of single source DSOs to SSRP efficiently, so that we not only store all answers, but compress them into a smaller structure, essentially. And what we obtained with this is a deterministic single-source DSO with logarithmic query time. And in the combinatorial setting, we get combinatorial preprocessing of m times square root of n plus n squared, which is exactly the running time of the Schirneck and Cohen algorithm. And our DSO only takes n to the 3/2 space, so we even shave a log factor there. In the algebraic setting, we get the preprocessing time that matches the algorithm of Grandoni and Wasilewska-Williams and has space m to the 1/2 times n to the 3/2. While this seems arbitrarily at first, we show that any single source DSO unconditionally must take this amount of space. But be aware that the upper bound is measured in the number of machine words, so log n bits, while the lower bound is in the number of bits, so there's still the factor of machine word in between, which is a log factor. But apart from that, our space requirement is tight. So how do we do this? We assume that we are given the output of really any SSRP algorithm, which is the shortest path tree rooted in S, and all relevant replacement distances. And from this, we want to construct in quadratic time a single source DSO taking the claimed space, the optimal space. The quadratic time is due to the fact that we have to touch every distance 1, but still it is small enough so that the known SSRP algorithms dominate then the complete preprocessing time. We start by computing a set of vertices we call pivots in such a way that every path in the tree has some pivot among its last square root n vertices. And we use this for a case distinction in our reduction. These cases are pretty common in the literature on SSRP. They appear under different names, but in this or very similar forms, they essentially appear in all works on SSRP. The first one is the near case, where the failing edge is between the last pivot x on that path and the target t. And the next one is the far case 1, where the failing edge is between the source and the last pivot, but the detour part of the replacement path merges with the original path before x. And finally, we have the far case 2, where the failing edge is between s and x, but the detour merges only after the pivot, so among these last square root n vertices. And in the following, I will discuss the far case 2 in more detail, because it is the most involved one in our reduction and is responsible, it dominates the preprocessing time eventually. First, note that in the far case 2, the edges between S and X have a monotonicity property in the sense that if you go from X to S, their replacement distance increase. This can be seen with this replacement path here. It skips not only the first few edges here, but the whole part until the pivot X. So the later edges here can only have at most the same replacement distance as those up in front. And if you do this for every replacement path in the far case 2, you get the monotonicity property. And the key claim in that case is that there are only very few segments that have the same replacement distance, namely a constant times the square root of capital M times n. And we will see once we bound the number of segments, we can also find them efficiently and store them efficiently. So the whole idea of the far case 2 is to bound the number of segments of different replacement distances. And first, it is easy to see that the edges in one segment all share some replacement path. Or put it the other way around, the reason why all edges in one segment have the same replacement distance is the same replacement path. We call this a representative replacement path. All representatives have distinct length and are, of course, at least as long as the original graph distance from S to T. So immediately from that, we get that the number of representatives that are short, namely smaller than the original distance plus 2 times the square root of capital M times N, is bounded by, well, this excess over the distance. So their number is at most 2 times square root of capital M times N. And to also bound the number of long representatives with the distance longer than that, we use what we call stubs. These are the first square root of n divided by capital M vertices on their detour path. So this blue part of the detour, and we claim that this part identifies the long representatives in the sense that these two stubs or any two stubs of long representatives cannot intersect. And if we have this, then there can only be square root of capital M times n stubs and so many long representatives. Why can they not intersect? Well, if you would assume that they do, then the edges they skip, namely this orange segment here, would have a replacement path starting from S until the beginning of the segment, going up the first stub to the intersection point, then going down the second stub and back to T. And this would give a replacement path of length at most this much, because on the stubs there are at most square root of n divided by m vertices, and therefore their weight, the weight of a stub is at most square root time capital M times n. So if two stubs of long representatives would intersect, we would get short replacement path, which we assume does not happen because otherwise the representative would not be long. So in fact, they do not intersect. And in the end, we bound the total number of representatives by 3 times square root of capital M times n. And also this is then the number of different distances in the far case too. And we can find these segments by scanning the replacement distances to which we have access due to our SSRP algorithm along this path. This takes linear time per target, and we can store them efficiently in space proportional to their number, which is this square root. And if we scale this up to all n targets in the graph, we end up with a quadratic reduction with the claimed space. It is also interesting to note that the same argument holds for vertex failures. There's a slight difference in that the constant factor increases from 3 to 5, but it's essentially the same argument to handle vertex failures. But the whole construction crucially depends on the underlying graph G being undirected, because we go up one stub and down the other stub in the opposite direction to create our contradiction. And indeed, this argument cannot be rectified for directed graphs. There are counterexamples to that. So what we have seen so far is how we can use the output of an SSRP algorithm to construct single-source DSOs taking near-optimal space. And our reduction is deterministic, but the best known SSRP algorithms so far are all randomized. And I claimed that eventually we obtain deterministic single-source DSOs. So in order to do so, we had to de-randomize the algorithms by Schirneck and Cohen, as well as by Grandoni and Wasilewska-Williams, to be able to plug them in and get a complete deterministic construction in the end. Also, our reduction takes quadratic time, so it essentially touches every relevant replacement distance once. And also, all SSRP algorithms need this time just to output all relevant distances. But if you would build a single-source DSO from scratch, from the graph without the SSRP intermediate, it might be that you can do faster than quadratic. It is known on very dense graphs that there are conditional lower bounds ruling out subquadratic time. Namely, you run into conflicts with the Boolean matrix multiplication conjecture. But on very sparse graphs, it could be that you can do better than quadratic. And indeed, we showed that on sufficiently sparse graphs with at most this number of edges, we can give a randomized construction for a single-source DSO that breaks the quadratic barrier. So we get truly subquadratic preprocessing time and the same query time and space as before. To wrap up, I showed you an improved deterministic single-source DSO for undirected graphs, and we showed that the preprocessing time, query time, and space is all near optimal. And we gave the first subquadratic preprocessing algorithm on sparse graphs. What is left to do? Well, the obvious question is, what can you do on directed graphs? It is known that for all pairs DSOs, where you can query any pair of vertices and not only distances to a single source, you have to have quadratic space. This is known. But this may or may not be true for the single source case. This is currently unknown. Also, it would be interesting to solve SSRP efficiently for vertex failures. So all known algorithms in that direction don't improve much over brute force currently. But if we had a very efficient SSRP algorithm for vertex failures, we could just plug in our reduction as is and get out of this single source DSOs for vertex failures, which would be very interesting. And with these words, I thank you for your attention.